So there are some really simple rules that can help us work out oxidation state. Let's take the first rule. It's the easiest rule of all. The oxidation state of any element is 0. So if in the balanced equation something is appearing in its elemental form, in other words, it's how you would find it on the periodic table, then it has to have an oxidation state of 0. That's a hard and fast rule. It hasn't lost or gained any electrons at all. So if you have oxygen as elemental oxygen, O2, the oxidation state must be 0. If you have hydrogen, even though it's H2, it must have an oxidation state of 0. Same with any metal, magnesium, for example, or zinc. What about chlorine? Nothing. Nitrogen, they're all as they appear in the periodic table. I'll leave you to do the others. What if we look at rule 2? The oxidation state of oxygen is always -2. Well, except in peroxides when it's -1, but don't worry about the peroxides so much. They won't come up in the exam. Most often you will meet oxygen, it's going to be as a -2 ion. That makes perfect sense because oxygen is in group 6, so it tends to gain 2 electrons. Even if it gains them through sharing, it's still got an oxidation state of -2 because it's got 2 extra electrons than it had before. So if we look at the oxygen in magnesium oxide, if we want to work out the oxidation state of the oxygen, it will be -2. If we want to work out the magnesium would be +2. But in this case, it's just asked us about the oxidation state of magnesium, of the oxygen. Oxygen in the zinc oxide, well, it's going to be -2, which would mean that the zinc was +2. What about the oxygen in Al2O3? Well, Al2O3, each oxygen is worth -2. So therefore the sum of all the oxygens is -2 plus -2 plus -2, which equals -6. So the sum is -6. That makes perfect sense because if you think back to chapter 5, each aluminium is worth 3 plus. So 3 plus plus 3 plus equals +6. So these charges, +6 and -6, balance each other out. So let's get rid of that, giving you extra information that you don't need. So each oxygen in Fe2O3, each one is worth -2. That's the rule. So the sum of all the oxygens must be again -6. So you can work out here which species of iron have you got. Well, it's got to equal -6 overall. So you've got Fe3 plus. Because 2 3 pluses makes +6 overall. I'll leave you to do the rest for the oxygens. Rule 3. The oxidation state of a hydrogen ion is +1. So in all of these, the HCl, the HBr, the H2SO4, each hydrogen is always worth +1. So that means when you've got more than 1 plus 1, let's take the sum of all the hydrogens in sulfuric acid, H2SO4, that's +1 plus 1, overall +2. Which again makes sense because we know our compound ions, that each sulfate is worth -2. So it balances out. Fantastic. This is no more difficult than it was in chapter 5, lesson 1. If you're still struggling with this, please go back to chapter 5, lesson 1 and revisit. So next rule. The oxidation state of any group 1 or group 2 metal ions is the same as its charge. Again, we learnt this before. So the magnesium is in group 2, so the oxidation state will be 2 plus. The beryllium is in group 2, so it's going to be 2 plus. Calcium is going to be 2 plus. So on and so on. You just look at the group number, and the same actually for aluminium. Aluminium can only ever be +3 because it's in group 3. So, rule 5. In a neutral compound, the sum of all the oxidation numbers is 0. That can seem like a bit of a mouthful. All it means is exactly what we practiced in Module 5, which is everything when added together must cancel each other out. All the negatives and all the positives must cancel each other out. Let's take this. Lead in lead oxide. Well, Rule 2 told us that oxygen was always -2. So the oxidation state of the oxygen is -2. We've got two of them. So -2 minus 2 equals -4 overall. All of the oxygens are worth -4. Therefore, the lead, in this case, must cancel out -4. There's nothing else to cancel it out. So the oxidation state must be +4. Let's try another one. The sulfur in SO2. Well, SO2 has oxygen in it, so each oxygen is worth -2 overall. Add them together, you've got -4 for the oxygen. Therefore, the sulfur must equal +4. Chromium. So chromium is a transition metal. It can exist as variable oxidation states. So we do what we know the rules for already. Oxygens are always -2. So you've got -2 times 7, which gives you -14 overall. Each sodium is group 1, so it's worth +1. So if you do -14 and you've got two +1s, +2 or +2, you're going to end up with -12. So the chromium in this case has to equal +12. Because it balances the charge out, and in a neutral compound the sum of all the oxidation numbers is 0. Let's try one more. The iodine in I2O5. Well, O5, oxygen is always worth -2, so you've got -2 times 5 equals -10. Now you've got two iodines here, so each one has to be worth +5, because +5 and +5 is +10. Now your brain right now might be going, does not compute. Iodine is in group 7. Hang on, if iodine's in group 7, it can only form a +1 ion, -1 ion, right? This is why oxidation number is not exactly the same as charge. You must follow these rules. There's no rule for there's no hard and fast rule for iodine, but there is a hard and fast rule for oxygen. So we just follow the oxygen rule, and we follow this hard and fast rule, which is in a neutral compound, the sum of all the oxidation numbers is 0. So it doesn't matter that the iodine has an oxidation state of +5. Remember, charge is similar to oxidation number, but it is not the same. The aluminium in Al2O3, well, let's do one more just for fun. Al2O3, well, we've got -2 times 3 gives us -6. So we've got two aluminiums, so the aluminiums must be worth +3. So that is the same as the charge, but it's not always the same. You just follow the rules rather than what you know about charge. Okay, rule 6. For polyatomic ions, the sum of all the oxidation numbers must equal the charge on the ion. So this is why it's so important for you to know the charges on your polyatomic ions. So the sulfur in sulfate, each oxygen is worth -2. That's rule 2, so it's very important. So you've got -2 times 4 equals -8. Well, everything altogether has to add up to -2. Well, to get from -8 to -2, I just need to add 6. So the sulfur must be worth +6. The nitrogen in the nitrate, well, nitrate's worth -1 overall. It's got a charge of -1 overall. Our oxygens, rule number 2, we must do rule number 2 first. So our oxygens are worth -6 overall, because -2 minus 2 minus 2 gives us -6. So everything's got to really add up to -1. So we need +5 to get us to -1. So the nitrogen in nitrate is worth +5. I'll do one more on this rule, but I think you're probably getting the hang of it now. The carbon in carbonate, well, you've got minus 2 times 3 gives you minus 6 for the oxygen. Everything's got to add up to minus 2 overall, so the carbon is worth plus 4. So the maths is very simple as long as you follow the rule. Here's a hot tip for you. When doing oxidation states with compounds that contain polyatomic ions, you can just use the overall charge of the polyatomic ion rather than working out the different elements independently. So, for example, the calcium in calcium hydroxide, you could work out minus 2 and plus 1 for the hydrogen. However, you know that OH is worth minus 1 overall. It has to be. That's a rule. So if you've got 2 minus 1s, you've got minus 2. So the calcium must be worth plus 2. The strontium in strontium carbonate, well, you know that your carbonate ion is worth minus 2. So you've got one of them, so your strontium must be worth plus 2. So this is again why it's so important to know the charges on your polyatomic ions. Please, 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 if you don't know them, go back and learn them. They are so valuable to you. All A-star students know their polyatomic ions and the charge. Okay, last rule, rule 7. Transition elements can have variable oxidation states. So you work them out last. Let's do this one. This is nothing new. This is everything that we've practiced before. So the iron in FeOH2, we know that iron can exist as plus 3 or plus 2, but we don't know which one we've got. So we use the polyatomic ion charges to work out which one we've got. Well, OH is worth 1 minus, so we've got 2 of them, so we need to make it worth minus 2. There's 1 iron, so each iron, well, my brain said 2, my fingers wrote 3, so each ion is worth plus 2. We know we've got the plus 2 variant of the ion. So the ion in FeOH3, well, OH3 must be worth minus 3 overall, so we know in this case we've got the plus 3 variant of the ion. So hopefully that has helped you out and you know exactly where you're going moving forward.